Parametric equations are typically of the form x equals f of t, y equals g of t, or similarly x equals like f of theta, y equals g of theta. The point is that we get the coordinates x and y by using a parameter t. And so x is defined by a function of that parameter t. Y is defined by usually a different function of that parameter t. And so one value of t will give me an x coordinate and a y coordinate. Often t represents time. And what we get out of this is, well, several things. This, as we go through this, the work in this section, we'll see how functions that don't pass the vertical line test can be expressed using parametric equations. So the x-coordinate is a function, the y-coordinate is a function. But we can also, using the parameter t for as time, we can say that for a particular time value, we know an x and a y coordinate for, say, an object in motion. It's also the case that the path of a curve defined by parametric equations has a direction as t increases. And often, almost always, we're going to indicate the direction of the curve when we graph it. We'll see an example here. Sketch the graph of the curve given by x equals 3t plus 2, y equals 2t plus 3. We're going to set up a table of values, and for the input t, we're going to get an output for x and an output for y. We use values like 0, 2, -2. And if t is 0, since x is equal to 3t plus 2, x would be 2. Since y is equal to 2t plus 3, if t is 0, y is 3. And you can verify that if t is 2, x is 8, y is 7. And if t is -2, x is -1, y is, if t is 2, x is -4, y is -1. When we sketch this, we're going to sketch it on the xy plane. The parameter t doesn't show up directly in our graph. Now when t equals 0 was mapped for x equals 2 and y equals 3, that actually gave us an ordered pair. And so we can plot the point 2, 3. And then when t was 2, x was 8, y was 7, again, another ordered pair. I had to adjust where my x-axis was for that one. And then our equations mapped -2 to the point -4, -1. Now when we plotted these, we plotted them, the first one was actually in the middle. The second one was farther on the right and above, and the third one was farther on the left and down. But that doesn't matter. What matters is, in order of increasing t, we have points that move along this line in an order. And so we can see that we would start at the point -4, -1, and then move up to the right toward the point 2, 3. I actually misspoke. We aren't starting at the point -4, -1. This keeps going on infinitely far in both directions. But as the points traced out when t increased, we went from lower left to upper right. And so I'm going to put an arrow on the graph to indicate the direction of the path as t increases. Now I have to avoid a habit that I tend to have here. When I'm graphing lines, I'll put arrows on both ends. But I need to avoid that here because there should only be one direction indicator for a graph like this. Sometimes it's useful to eliminate the parameter. Now, there's not any one way to do this. We look at the equations that we have and we see, how can I express what I'm looking at as an equation that only has y and x. In this case, it makes sense to me to take x equals 3t plus 2 and solve for t, thereby getting x minus 2 over 3 is equal to t. And then do the same thing with y. So y is 2t plus 3, and so y minus 3 over 2 is going to be equal to t. Since these two fractions are both equal to the same thing, t, they must be equal to each other. And so it follows that x minus 2 over 3 is equal to y minus 3 over 2. Since we can solve this for y, we may as well. and we end up with y is equal to 2/3 x plus 5/3. I'll leave it to you to verify. And so what we can see then is the line that we just graphed has a y-intercept of 0, 5/3, and the slope is 2/3. I'm going to circle that result. Why do we say circle? I ellipsed the result, right? I put it in an ellipse? Never mind. All right, next exercise. Sketch the curve given by a pair of parametric equations and eliminate the parameter. And the curve is defined by x equals t squared and y equals t cubed. And I'd like for you to pause the video here and do as much as you can to both sketch and then eliminate the parameter. Putting in various values for t into the equations that give us x and y, I see that, for instance, -2 is mapped to the point 4, -8. -1 is mapped to the point 1, -1. 0 maps to 0, 0. 1 maps to 1, 1. And 2 maps to 4, 8. Those are the points that I've plotted here in my graph. And as t increases, the easiest way to look at this for me, or for me to describe it, is to say that y increases. And so our graph goes from the lower to the upper. And I believe this is called a kappa curve because it resembles the Greek letter kappa. And I've put little arrows on the curve indicating the direction in which the curve traces out as t increases. As far as eliminating the parameter, since x is equal to t squared, we know that t is equal to plus or minus the square root of x. I hope you remembered the plus or minus. We can put that value of x into the equation y equals t cubed. The result is that y equals plus or minus x to the 3/2. We need both plus and minus because, as we can see, we have curve both below and above the x-axis. So this is not a function of x, right? Y is not a function of x. And our graph does not pass the vertical line test. We can see that. However, each coordinate x and y is a function of t. And so by expressing things in parametric, using parametric equations, we'd actually be able to do calculus on something whose graph doesn't pass the vertical line test. That's a preview of coming attractions for later in this chapter.